Good afternoon, everyone. Welcome to the 2013 T.C.Wollan lecture. This year it is a part of a series of events called the Joint T.C.Wollan and Nobel Peace Prize Lectures. These events are sponsored by the T.C.Wollan Memorial Distinguished Lectureship, named to honor the memory of Thomas Carl Wollan, one of the founders of the mathematics program at Concordia. The lectures are also supported by the departments of physics, political science, religion and sociology, as well as the global studies program, division of sciences and mathematics, academic affairs, president's office, and Concordia's alumnus Brent Colby, who made a donation in Carl Bailey's name. Our speaker is Francesco Calogero, a renowned Italian physicist. He graduated laurea in Fisica, cum laude, from the La Sapienza University of Rome in 1958, and since then has been associated with the university. He became a professor of theoretical physics in 1976. Francesco Calogero has contributed to multiple fields of mathematics and physics, among them quantum field theory, scattering theory, nuclear many-body problem, solvable dynamical systems, integrable nonlinear evolution PDEs, special functions, finite-dimensional representations of operators, techniques of the numerical computation of the eigenvalues of differential operators, and other. I will stop here. His scientific publications include close to 400 and also 4 books. Francesco Calogero is active in the community of scientists concerned with nuclear disarmament. From 1989 to 1997, he served as Secretary General of the Pugwash Conferences on Science and World Affairs. And in that capacity, he accepted, on behalf of Pugwash, the 1995 Nobel Peace Prize, awarded to Joseph Rotblat and to Pugwash, for their efforts to diminish the part played by nuclear arms in international politics and, in the longer run, to eliminate such arms. Tomorrow and on Thursday, Francesco Calogero will speak on a nuclear weapon-free world and the social responsibility of scientists. The schedule of events is available on the brochures that are passed around today. They look like this. There are some at the door. Also on posters around campus and on Concordia webpage. Today, Professor Calogero will speak about cool numbers. Let us welcome our speaker.
Beginning from something very elementary, the difference between a rational and an irrational number, and then rational representation. I will always talk about the rational representation in base 10, the one that is used in supermarkets. So a rational number is the ratio of two integers. So for instance, 17 over 28 or 10 over 81. An irrational number is a number that cannot be expressed as a ratio of two integers. For instance, the square root of 2, which is written this way, or the ratio of the length of the circumference of a circle to its diameter, which is traditionally indicated with the letter pi. The decimal representation of every rational number is a decimal number with an integer part and a decimal part. It generally contains a non-recurring sequence of digits followed by a recurring sequence of digits. So for instance, 17 over 28, which can also be written in this form, 17 over this is the representation of the number 28 in terms of its prime decomposition into primes. So 2 squared times 7 is 28. The decimal representation is this one, so it is 0.60. And then there is 714,285, which is repeated an infinite number of times. And any rational number has a representation of this type, except that sometimes the non-recurring part may be missing. For instance, this is an example here. 1/3 is 0.3333 number of times, or the recurring part may be missing. For instance, 1/2 is 0.5.
If I may interrupt, I think you forgot to turn on your microphone.
Thank you. This is the mathematician part of it. But I will not begin. I hope everything heard what I said until now. By the way, there is a very simple rule that tells you, given a rational number as a fraction, a numerator and denominator, how long is the recurring part and the non-recurring part, and how long is the recurring part. I will just remind for you that this is a simple rule. For the non-recurring part, this part here, the length of this part is given by a very simple rule. You have to look only at the denominator of this number, look at the decomposition of the number in the denominator in terms of primes, and then look at the exponents of the numbers 2 and 5, if they appear. And then the highest exponent of these two numbers give you the number of digits in the non-recurring part. So in this case, you see the exponent is 2, and there are 2 digits here. And we'll see maybe other examples later. Okay. Now, I'll go ahead like that. Yes. If instead you have a irrational number, so a number that cannot be written as the ratio of 2 integers, then the decimal representation of such a number has an endless sequence of digits in its decimal part, which is not repeated. So it is an infinite string of numbers. For instance, a number that will play some role in the rest of this talk is a number that is called the Champernowne constant. I will say something more in a moment about this. And it is the number whose decimal representation is just this very neat one. I lost this. How do I do this? Yes. So it is called C10, but you can forget its name. C, I think, it stands for Champernowne. And it is just 0.123456789111213 ad infinitum. So it is an irrational number because of, and this is it. By the way, notation, when I write numbers in this decimal form, sometimes there will be blanks here. They have no mathematical significance. It's merely a aid for a seeing aid. And when there are dots, it means that you have just to continue in an obvious way. So in this case, the obvious way is just to continue with the series of the integers. And of course, this is a number as any other, an irrational number. For instance, it is clear that 0.123 is less than C10, and that C10 is less than 0.1235, because you see this 0.123, and then you have something after 4, so it's larger than this, but this 4 is less than 5. And now I come to the definition of the topic of my talk, which is cool numbers, and it is not a very precise mathematical definition. A cool number is a number that in its decimal representation has a look. It's a question of look, which is cool. This is a term used by young people. I'm not a young person, but nevertheless, that is the definition. And I think it will be clear to you in which cases this is applicable, just as it is clear to you who is cool and who is not from the way he or she is dressed. And of course, the Champernowne constant is a preeminent example of a number which is cool. In this case, an irrational number. It's cool because it has a very remarkable representation as a decimal number. Go ahead. Yes. And now let us see how a cool number, a rational cool number, which I call cool, or you might say rather cool, emerges. And so I take 10 over 81, and let's see if you develop this number as a decimal number. So first of all, you have 0.1, and then it will of course, continue, you see, and it is approximately 0.1. And if I go ahead, this is the next step. It would be nice to make this really as a division, but I did not know exactly what kind of way in the United States children are taught to make a division. So I just wrote it in this way. So I go ahead in making this 10 divided by 81, and the next digit you get is 2. So approximately this is 0.2. And then the next one is 0.123. And the next one is 0.1234. By the way, you can play this as a parlor game. You can try to entertain an audience and ask them to do this operation. You could do this in the past. Nowadays, people will take a computer and they immediately get all the digits, and so the pleasure of seeing these digits come out is lost. These are the digits that come out. You see 0.1, 2, 3, 4, 5, and then it continues, and it goes up to 0, 1, 2, 3, 4, 5, 6, 7, 9. So there is no 8 there. And let's see what I wrote. This is again this whole series. This is what goes up to this figure. And so 10 over 18 is approximately this number, because the next one is a number which is less than 5. And let's see what I have here. Yes. This is now continuing to make the division. You get 901, then you get 9012, then you get 90123, and then you get 9, 0, 1, 2, 3, 4. And this is just by doing the ordinary division that a schoolboy learns how to do. And this is the final result. The final result is 10 over 18 is this number in which the notation I use with the square bracket indicates the recurring part. So it is 0 point, then you have 1, 2, 3, 4, 5, 6, 7, 9, 0, and that's repeated an infinite number of times. That's 10 over 18, and I claim that it is rather cool. Rather cool. So you see, in this case, the number of digits inside the square bracket is 9. You have 9 digits, and you have no recurring part, because indeed the denominator here, 81, is just 3 to the power 4. So there are no in the prime decomposition, there are no powers of 2 and no power of 5. So 0 non-recurring part. It is only the periodic recurring part. Now we can give a name, R00, but that maybe will be later clear. That's not very important. This as I've written it again. And you see, approximately this number is 10 over 81. It is 0, 1, 2, 3, 4, 5, 6, 7, 9, 0. And you might not like this, because it's something, there should be an 8 there, you see. So how can we try to get an 8 there? And so I wrote again the same number here. And then you see, to get an 8 instead of a 9, I have to subtract something here. And so this is the 9th place, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have to subtract, the first guess is, let's subtract 10 to the minus 9. 10 to the minus 9 means that you have only a 1 in the 9th place. It's 1 over a billion. So it is 0.00000000001, 9th place. So we just make this subtraction, and we get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So improvement. And then 1, 2, 1, 2. So maybe we don't like this so much. We would like to have a 0 there. And so in order to get 0 instead of 1, you must subtract something slightly bigger than this, so that you get a number that is smaller. And so let us try, and I call this an educated guess, because you will, at this stage, ask yourself, how did I choose this number? I subtract not 10 to the minus 9, but something a little bit bigger. And so it is 10 to the minus 9 times 3340 divided by 3262. So it's a number a little bit larger than 1. And this can be written as a ratio, and it is this ratio as a fraction. I wrote in longhand. This is written in terms of the numerator and the denominator are, there is the prime decomposition of this number. And now let's see how it looks, the decimal representation. And the decimal representation looks pretty cool. 1, 2, 3, 4, 5, 6, 7, 8, and then the recurring part starts, and it is 9, 10, 11, 12, 13, and here there are many dots, but it means 14, 15, up to 95, 96, 97. Then there is no 98, 99, 100, 01, 02, 03, up to 07, 08, 0, and that's the recurring part. So it's pretty cool, isn't it? I mean, it's now it's really not so trivial, because so the non-recurring part of this number, you see, it's 1, 2, 3, 4, 5, 6, 7, 8. There are 8 digits, and this corresponds, you see, to the fact the rule was that you have to take the largest exponents among the prime numbers in the denominator, so it's 2 to the 2 or 5, 2 to the 7, 5 to the 8. So 8 is the largest, and you have indeed 8 digits here. And then you have this recurring part, which is the recurring part. If you count digits, it's 198 digits. Now I will show you some other cool numbers, and then I will show you how to manufacture cool numbers. So in particular, how to find, rather than by trial and error, how to find this particular number and how to find many other cool numbers. But first, I think I'll show you some other examples of cool numbers manufactured in this way. So you may forget about the names given to these numbers. This is 100 divided 9,801, whose representation in numerator and denominator in prime numbers is given here. And this is now the decimal representation of this number. See, 0, 1, 0, 2, 0, 3, and then all the way 0, 9, and then 10, 11. So these are all two-digit numbers, starting from 0, 1 and going all the way to 97. Then 98 is missing, and then you have 99, 0, 0, and then this is periodic, so this is the recurring part. You see, in the denominator there is no 2 and no 5, and so this number does not have a non-recurring part. So that's it. It's pretty cool, as you can see. Again, the number of digits here is, if you count them, it's 198. So the recurring part is made of 198 of this very peculiar form, and then they are repeated an infinite number of times. Another cool number is a bit similar. It's 1,000 divided by 998,001, so this big number. This is the representation in terms of primes of numerator and denominators. And this is now again the rational, the decimal representation of this number. You see now this is in terms of numbers written as triad, 001, 002, 003, and then all the way 009, then 010, 011, 099, 100, and so on. Again, now you get here 997, 998 is missing, then 999, then 000. Again, this is the recurring part, and there is no non-recurring part. There is no denominator here with a 2 or a 5. The number of digits in the recurring part this time is 2,997 digits. So this, of course, as you understand, would be not easy to do by hand, and not easy to find by trial and error, even using a computer. And I think I still have another example. Yes, this, again, I forget the name. This is, the numerator is 1,000 minus 10 to the minus 2,997 times this number, divided by this number, which is 999 to the power 2. And this is this decimal number. You see, in this case, there is no recurring part, so it just ends here, and it is just 001, 002, 003, all the way 099. Oh, I've repeated it. I should not have repeated it. There's a mistake here. 100, 101, and so on, and so on, and so on, all the way to 999. In this case, there is no gap, so to say. Again, in this case, the number of digits of the non-recurring part is 2,997, and there is no recurring part. And there is still another one. This one is this number here. You see, the written as a fraction. It is pretty long, but the rule to see if a number is cool or not is that the number of digits here should be much less than the number of digits here, because otherwise you could just choose a number that has, a string of digits, and then go do the reverse, obtain the representation as a rational number, but then the rational number will also have a very large number of digits, whereas here, you see, although there are quite a few digits here, the number of digits here is much, much larger. It's 2,997 in the recurring part. So almost 3,000, and this is, I don't know how many, 20 or something, so it's a very big difference. And all these zeros are just put in order that you start with 0, 0, 1. So this number, it has to be of the order of 100s. And again, you see, it's quite cool. It's quite cool the way it goes. There are 16 non-recurring digits, which are this here, and this corresponds to the fact that in the denominator, if you represent it in terms of its prime decomposition, you have a 5 to the 16, and so this is, of course, well known. These are very old results in arithmetic. Now, before I go on to show you how to obtain these formulas, I want to tell you something more. And, you know, I wrote this as an amusement, and then I sent it to a journal which is called the Mathematical Intelligencer. And then I got back a referee report, which was positive. They said these are interesting, but then added many things which I didn't know at all. So I learned some things from this referee who knew much more than me of the general area. And one thing I learned, which not many people know, no physicist knows, and not so many mathematicians know, what is the definition of a normal number. This is now a precise definition in mathematics. A normal number is an irrational number, so in decimal, the normality refers to its decimal representation. And for simplicity, we always look at the decimal representation in base 10. So an irrational number is an infinite string of numbers, and it is called normal if, in some sense, it should have nothing peculiar. And having nothing peculiar, the precise mathematical definition is that if you take any digit, say 7, it should appear only 1/10 of the time, the natural frequency of 10. If you take 22, it should appear 1/100th of time, because it's a natural frequency. If you take any other number in this infinite sequence, it should appear with a frequency which is exactly the correct one for, so if it has 4 digits, it should appear 1 over 10,000 times, and so on. You see, it's a precise definition, but it's a definition that entails that it is very difficult to decide whether a number is normal or not. And to this day, there is no proof that pi is a normal number. Pi, of course, has been computed to billions of digits, and it looks normal, but it's one thing to the fact that it looks normal, so that there doesn't seem to be any sequence that is privileged in some way. It's another thing to prove it, and it's a very big challenge to prove that pi is normal. If any young person in particular were able to do that, he would become a professor in one step in number theory. The same with e. The base of the logarithm, so to say, the natural base is of course, believed to be normal, but it is not proven that it is normal. It is very difficult to prove that a specific number is normal. And now comes what I consider is a big surprise. The first number that was proven to be normal is this one, the Champernowne constant. Incidentally, Champernowne proved this result as an undergraduate in Cambridge in 1933. So, a challenge for young people. And he has shown, there is a proof, there is a paper, the paper is this one, which is here, the construction of decimals normal in the scale of 10, in 1933, the Journal of the London Mathematical Society. It's a 7 pages paper. I haven't read it, I must confess, but I learned about all of this from a referee of the amusement of the paper I wrote about cool numbers. And so this is, it is a normal number. In some sense, it's not as strange as it might look, because you would say this is not normal at all. It's very special, very peculiar, but it is normal. And you can convince yourself of that if you, maybe with a computer you can take this number with many, many billions of digits, and then look at a piece, and then you will see something that looks absolutely random, because it will be the inner part of a very big number of the order of many billions or trillions if you go far enough, and that will have nothing special. And so, in fact, this sequence of numbers has nothing special in this sense. Every digit and every subdigit appears with this correct frequency in this infinite series. Okay, now I used this number. I didn't know it was already known, and it was the Chamfer-Noun number, but I used it to obtain these cool numbers. And let me go on the other side again. And I used a representation of, now it's becoming a little bit, it's elementary mathematics, but a little bit less elementary. I wrote down a representation of the Chamfer-Noun constants, of that number that was over here, as a series. And the representation is, well, you have first this 10 over 81, which would correspond, in fact, to k equals 0 in this series. I just wrote it out. And then you have this infinite series, and which I computed. And let's, for a moment, forget the precise. You see, both the exponent alpha of k and the beta of k are given by explicit formulas. Alpha of k is rather simple, beta of k is a bit more complicated. And first of all, beta of k, it looks complicated, but in fact it's a number which is always of the order of 1. See, beta 1 is this number here, beta 2 is this, and the limit of beta of k as k goes to infinity is 1. So this number is of the order of 1. And this is a very fast converging series, because the alpha k grow very fast with k. You see there is 10 to the k here times k. So alpha 1 is 9, alpha 2 is 189, alpha 3 is 2,889. So you see it grows very, very fast. That means that if I now look at this series and I truncate this series, so instead I truncate it, say, first of all, I could truncate it by just taking this, and then I have the very first number that I have shown. And you see this one, the next one starts with alpha of k for k equal 1. It is already 9. So this is already a number of the order of 10 to the minus 9, which was the corrections that we had. In fact, I think beta k, you see, just this magic number 33403267, which I had to subtract from this in order to get a much cooler number, a number with a lot of digits which were regular. And because what happens is that if I stop this series at k equal 1, I neglect what comes next. The terms that comes next is already a term which has an alpha 2, which is minus 189. So it is a very small number that has that starts well, it's very small. It's it has a lot of zeros before it has any digit, and therefore, if I stop there, I have a number that is very close to the Champer noun constants, and therefore has this remarkable look, and so on. You can go on. And so that's the basis for obtaining the numbers I gave there. And likewise, you can do the same thing starting, rather than from the Champer noun constant, from another number. Maybe I should go back here. From another number. For instance, in this case, in order to manufacture this number here, you start from the infinite series, 01, 02, 03, 04, 05, 08, 09, 010, 11, 12, infinite series, and then you represent this as a converging series of this type and truncate, and you get this number. So the procedure is very simple, and what remains to see is how you get the formula. I have to go ahead. No, I have to go the other way. Yes. How does one get this formula? And this is a little bit more technical. I will show you this, and then I will be done. So where do I do it in this side? Well, first I say that analogous, rather cool rational numbers, including those displayed above, what I had begun to say, but I forgot that it was here, can be obtained in an analogous manner starting from other cool irrational numbers, analogous to the Champer noun. For instance, this one, which is now an irrational number, infinite sequence, but then the trick is that you represent this as a series which converges very fast, and then when you truncate the series, you neglect the term of higher order, you get a number that approximates very closely this number, up to, say, 100 digits, and therefore has a remarkable look. So the last task is now to prove the formula that I have shown. And so we start from this number, and we want to represent it as a sum of this type, an infinite sum, because this is an infinite number of digits. And you see, how do you do it? You say that the first digit here is 1, so this sum will have 1 to the power, in this case it would be 1/10. And then the second digit would be 2, and it would have a power minus 100. I have indicated this with Pn, so I have to find what these Pn are. The third will be 3 times 10 to the minus 3, 1,000, and so the third Pn will be 3. And so the first will be just 1, 2, 3, 4, 5, corresponding to n. But then when you come to this, it's a little bit more complicated, because then here you have the number 10, and there are two digits here. So you have to be careful in how to construct this number Pn. And to construct it, it's convenient, first of all, to rearrange the sum that we had. You rearrange the sum by summing on numbers, each of which has the same number of digits. So you have first the numbers of the terms with 1 digit, then you have the terms with 2 digits, then with 3 digits, and so on. And so this is now the sum over numbers of k digits, and this is now the other, the sum in which you sum over the numbers that have the right number of digits. So for instance, for k equal 1, this is just from 1 to 10, because k is 1, so from 1 to 10 you have numbers with 1 digit. The next will be numbers of 2 digits. It corresponds to k equal 2, and then it goes to 2 minus 1 is 10, and this number is 100 minus 1, 99. So from 10 to 99, these are numbers with 2 digits, and so the number is there, and then this is the 10 to the exponent, and this p is the same as before, but now I indicate this as p, a function of n and k, but it's the same p as before. And now you have to find a recurrence formula for this Pn of k, and you can convince yourself that the correct recurrence formula is the one written here. The Pn of k is the p of 10 to the k minus 1 plus k times n times. To convince yourself, you have to think a little bit about this. And once you have convinced you that this formula corresponds to this fact that I have described in words, then the rest is sort of elementary computations. You write that P and K is Kn minus Q of K, and then for Q of K you get this recursion, which is a very elementary one-term recursion which you can solve exactly. And so you have the solution for Qk, and then you put all this information inside here, and you get the formula that we had before with this B of k, which is written there. And then B of k you can compute, because this sum, it's easy to compute. It's essentially a geometric sum, or the derivative of a geometric sum. And so you get this expression for bk, and that's the proof. And this is the end of my talk. Well, yes, there is. The C of 10 is the Champernowne number in base 10. So it is the decimal base. So it is 0.123 up to 9. For instance, C2 would be, you would have to write the number in base 2. With the same kind of rule. And in fact, in my paper, I treat the general case with an arbitrary base, but that makes things somewhat more complicated. And by the way, as far as I understand, if a number is normal in one base, it is not necessarily normal in another base. So the property of being normal is not invariant on the base. It's really something that has to do with the decimal representation and to go from one to the other. It's, as far as I know, maybe I'm not a specialist in the matter, but this is. So this was the origin of the name C10, is because it is the Champernowne number in base 10. Yes? Yes. Because they are not. No. Well, but being normal is a property of the decimal representation, not decimal, but the representation decimal in that base, and. I think so, yes. They are all. I think that the proof of Champernowne is in any base. It's not in base 10. I wouldn't swear, but I think it is so. Yes, I think these are all normal, but cool. So you see the difference between pi and the Champernowne constant is that probably they are both normal, but the Champernowne number is cool also, whereas pi is not cool. If you look at the digits, they have no special significance. Although, of course, as in all rational numbers, since you have an infinite sequence of numbers, you can find in it whatever you like, including the entire Bible. I mean, because that's a property of infinity, that infinity contains any sequence. So, but it takes some time, of course, to find it, but it's there. Yes, this converges to 1. Yes, yes. It's. I think it's easy to see because the dominant term here is this 10 to the k plus 1, and then you have 10 to the 2k and 10 to the k plus 1. These are smaller, and below you have 10 to the k and 10 to the k plus 1 square. So we have twice 10 to the k, twice 10 to the k plus 1, which is what you have here. So you see that it converges to 1, and it converges pretty fast. This is because it is done in base 10. If everything were done in base 2, the numbers would look much less cool because they don't converge so fast. You see, this series converges very fast because of 10. So the exponents send it down very fast. And so if you truncate it at the second term, you have over 100 digits, which are already remarkable. If you are in base 2, you will get only 4 or 5 digits, which are remarkable. So it's a property of a large base to produce cool numbers very soon. In any case, don't forget 10 over 81 as being a special number, because that's easy to remember. By the way, it is also remarkable as a fraction, because it is 10, which is 2 by 5, divided by 3 to the power 4. So it's constructed with the first 4 numbers, 2, 3, 4, 5. So easy to remember it. It's 2 divided by 3 to the power 4 with another 5 on top. It's the magic of arithmetic, elementary arithmetic. Okay. My next talks will be about less amusing.